Yeah, so that the second episode, part 2 of a talk about mechanisms of plasticity and flow. So what we did last time, we looked at AQS, athermal quasi-static simulations in detail. And if you remember, we learned a number of things. One thing was that the flow plasticity, so these AQS conditions correspond to a solid at very low temperature, at very low strain rates. And in these conditions, we see that the relaxation proceeds, the flow proceeds by local rearrangements. These local rearrangements gives rise to long-range Eshelby strains or stress fields. And because of these long-range Eshelby strains, an event can trigger a secondary event and leading to avalanches. And avalanches are caused by, in fact, two things: by the existence of Eshelby stresses, and by the fact that when you strain a system, you bring lots of these region near instabilities, and so you are creating an enhancement of the you're populating. You're creating a population of very marginal near instability regions. So I wanted just to add, I will first go a bit quick just to show you a few things that people are doing about, so that's what we've been looking at, this AQS limit. I wanted just to show you a very few things that can be done with AQS, that are currently done with AQS. There is one, I'll go very briefly on this. There is essentially this is in steady flow. And if you are in steady flow, you unload and reload. You follow these kind of curves. And if you load backwards, and here I'm plotting in red the backward stress curve, you have something much softer. So if you shear and unload and reload, you may have you have what is called a Bauschinger effect. Bauschinger effect was initially identified in crystals, and it's related to the fact that when you reload something that has been unloaded, you have something which is stiffer than if you reverse the loading response. And all this is a signature of this marginality. I will not go into detail. I just want to point out a number of works by Patinet et al. And an idea which also was proposed by Podim. There are people who are trying to extract a region from a material in order to measure the local yield stress, and you can construct local yield stress maps, and you can basically look at show that the plastic response indeed is related to the low yield stress regions. And there is a whole activity on this kind of research topic. I will pass on that. I also want to mention many works by Shrikant Sastry, and actually Giuseppe Foffi also contributed to that, where people are using AQS to do cycling. And in doing that, you can start to get an understanding of the cycling response of material. One thing which is particularly interesting here is that if you make a very small cycles, in fact, you can reach a regime where the system displays an elastic, a cyclic reversible response. So you create cycles. And if you start to shear with a larger amplitude, you end up to reaching regimes where basically the system, you create plasticity and the system starts to flow. So you have a transition between the short cycles where you can, short strain amplitudes where you can create cycles. And when you go to larger strain amplitude, you start to create plastic flow. So these are just fields I want to mention that they exist. And I encourage you, this is, for example, a review paper where you will find lots of interesting information if you want to look at that. And this is a way to look at we heard a lot about G prime, G double prime. This is a way to understand what the underpinnings of the oscillatory response. There are lots of works about now. I talked essentially about steady flow. There are lots of works now that have looked at the onset of flow. And if you start, for example, from a very relaxed, these people here have an algorithms to create a very relaxed glasses. And when you start from a very relaxed glass, you can have a response which is fragile with the formation of a crack. And all this is again in AQS. So all this is based on AQS simulations. and allows you to look. And so essentially what you see that when you load elastically, you start to have a bit of plasticity, and then you have some kind of enhancement of the plastic activity before you reach the steady state. So there are all sorts of things you can do with EQS simulations. I will pass on that. I wasn't sure to show this movie, but I will because of the last talk. This is something we did where we are compressing a film. We have a very thin film which is strongly adhering here on the surface, but it slides on the surface. We compress it in the EQS limit, and what you show is that you have formation of ridges. And the formation of ridges is not a buckling instability. In fact, it's just an EQS response. It's result from the accumulation of plastic activity. And so what happens is that you have elementary events which are some kind of burst, and you can do the Eshelby analysis, and you can show that this burst leads to the formation of avalanches that are transverse to the compression direction, and that leads to the formation of regular ridges. So, okay, I just wanted to mention these. These are different examples of things you can do with the EQS simulation. It's an active field of research. But what I wanted really to address, to focus on today, was, so these are these case studies. What I wanted to focus on today was, it's actually related to a question that somebody asked, and which is a natural question to ask, is why is this relevant to the real life? Because the EQS response corresponds to a very strange limit where you say you are formally at low temperatures, so you minimize your energy, you are always looking at solid states, and you strain the system infinitely slowly. And somebody asked, but what about thermal fluctuations? And maybe you could also ask, and what about finite rates? And so I would like you to try to formulate, before I talk, to try to formulate your own idea, but what do you think? What do you think about how robust this picture we have from quasi-static simulation that I developed last time, how robust do you think it is to now if I will go to finite strain rates and finite temperature? Who thinks that this will rapidly be destroyed? Nobody? Who think that, so you all think that this will exist, but up to what? Up to the liquid? So in the EQS limit, we have events, Eshelby events, generating avalanches. Do you think avalanches exist at all temperatures? Who thinks avalanches exist at all temperatures? You think? Okay. Yeah?
I think in the liquid they probably relax instantaneously, while in the solid they propagate long range. Instantaneously and locally, while in the solid probably they propagate long range. But I think that KT probably what is needed in a real liquid.
Okay, that's very good. I mean, it's very good you try to formulate some insight, because this is how you can see what I say, which is different. And I think this is really the best way to understand. So one thing we can do is first, in order to explore that, is I don't like to introduce two parameters at the same time. It makes me nervous. So we introduce one parameter, and the only parameter you can introduce first is the strain rate. So what you can do is say, let's look at damped dynamics. So damped here, you notice that I've seen many people running damped dynamics where they add a viscous drag on the velocity. That's a bit a problem in terms of the underlying physics. When you add, here we add a drag on the difference, and when you do that, what you can show is that you allow sound propagation at large length scales, which is what you want to do in a solid. We are studying atomic solids, and these atomic solids, sound has to be able to propagate, And the damping is really a local mechanism. Damping here results from the emission of acoustic waves, from the emission of sound. And so you have to have drag on the difference of velocities. And the detail, these are details which are not very relevant. But so we look at, and so the first thing to do is just to get a picture of what happens. I'll write these non-affine, I discussed about non-affine, so I'll draw the non-affine velocity field. I'll make a movie of the non-affine velocity field in a sheared system. So this is my system, is gonna be sheared. I will look at the very small strain rate. So when we will see later, I can just announce that it's a small strain rate that corresponds to being close to the quasi-static response. I write temperature here. The temperature is just the kinetic energy. You have some kinetic energy because you introduce now a finite rate, and it's very small. And so it's in that sense that we are in very low temperature conditions, in athermal-like conditions. And that's what we see. So what you see is that you have, so again, this is the non-affine velocity field. What you see that you have when you see big arrows, it's because in the core of events, this velocity field has to be strongly amplified if you want to see the very long range things. And so the large arrows are when you have a rearrangement, you have a lot of motion in the core of these rearrangements. And then you see when you have a rearrangement, then you see things that propagate out of these rearrangements. And what you see is sound. So these are sound waves. So here you really see the same mechanism I was discussing before. You have rearrangements. These rearrangements are local, and they give rise to sound waves. And the sound waves are how you establish these Eshelby fields, right? Because Eshelby fields, again, they are related to the mechanical elastic balance, and they propagate by sound waves. So if you look at the stress, here this is the stress field. This is the time derivative of the stress field, and you see you have these events. And well, you might, it's hard to see, but if you look, you might convince yourself that you tend to have events which have this quadrupolar structure. Yes?
Looking at the previous picture, you say these are sound waves. So in an overdamped regime, you would see nothing?
So if I was overdamped in the sense that I had a drag here on the velocity, not on the difference, but if I would see that, yes, you would damp the sound waves, and then you would have a diffusive propagation of the information of the mechanical balance.
To me, what kind of drag do you have, and what kind of drag you don't have in this simulation?
Well, I have a drag here on the velocity difference. What it means is that you damp the short wavelength, and so you extract energy out of rearrangement, but you do not. So the damping here is only on the short wavelength. You don't damp the long wavelength, so you allow sound to propagate. And this is what you need to do if you want to model the damping mechanism in the absence of bath for a solid at low temperature. Right? Because the mechanism of damping in a solid is that when you have a rearrangement, it emits sound. And it's the dispersion, it's the scattering of sound which extracts energy out of where it even happened. Okay? And so that's what we are seeing. You have a rearrangement, and this rearrangement, the energy coming from this rearrangement radiates and then spreads out.
But this force that you show here, this is not the scattering. It's something different. Or am I misunderstanding?
It is not.
Is this term Fij is the difference of velocities? Is this supposed to model the scattering? Or?
It models the scattering in the sense that you are damping here. We could look at the detail here, but if you write a continuum equation equivalent of that, you will have a gradient of velocity in the damping. You don't damp proportional to velocity, but to the gradient of velocity. And when you want to look at, when you do the analysis of so you write a wave equation with a damping on the gradient of velocity, not on velocity. And when you do this, you guarantee that you do not damp the long wavelengths, which is absolutely crucial to get sound propagation. If you do anything else, you will damp the long wavelength. Okay, that's all I'm saying. Right? So you have these events. They create sound waves. This is the same thing at a higher strain rate. So the thing is a bit more blurry. But you still see events, many more. And you can also see strains, large strains, and waves that are emitted. So from the dynamics, if we look at the non-affine field, we see events that retain essentially the same nature. Yeah.
So from the previous model, you added two things at the same time, both the temperature and the damping.
Both the
temperature,
yeah,
and the velocity difference damping.
There is no temperature at all. There is only shearing and these damping forces, and that's it. There is no bath. And this is why this is a way to approach the very low temperature regime.
So the energy is coming only from
the shear. So the point is that you're shearing the system. Thank you for your question. You need to dissipate this energy. You dissipate it with a way which guarantees that you allow sound propagation. Right? And the only energy comes from shearing. You have an effective temperature which is very small, and which shows that you indeed approach these very low temperature limits. Okay.
Sorry.
So, yeah.
And the characteristic time in which this energy was dissipated.
You can associate to this a characteristic time, which is a fraction of the Leonard-Bloom's time. So it's really the time of a rearrangement. So within the time of a rearrangement, you locally dissipate the energy. And at longer range, you don't dissipate. You allow sound to propagate again.
Okay.
So you have a local mechanism of energy dissipation with a short time scale, which corresponds to the time scale of a rearrangement. So essentially, it means that at the time scale of a rearrangement, you allow the associated energy to be damped, and then you get you can see the resulting mechanical signal.
This might be extremely naive, but why you cannot be in the under-damp regime, right? Why you cannot have just gamma V, just regular local friction, and let the inertia do the job?
No longer you damp the long wavelengths.
But you dump it, but you still oscillate, meaning you still propagate the sound wave.
You might see something, it might be interesting in some context, but you damp the long wavelengths. So here I'm trying to model an atomic solid in a low temperature. I'm trying to access the low temperature limit of an atomic same solid. So I need to have the proper damping mechanism. If you were in a suspension, I have nothing to say. Okay, so the question is, so the point is that from the dynamic of the velocity field, we still see events that retain the same nature as we saw in AQS. As we guessed from AQS, here we see them. We see acoustic propagation. But still, the question remains. I mean, we have not seen avalanches yet. I've not shown you avalanches. If we look at the stress of this system, we see a very nice Herschel-Berkeley law. beautiful Herschel-Berkeley. It really fits perfectly a square root of gamma dot. If we look at the stress fluctuation, if you remember from last time, I told you the signature of avalanches was that the stress fluctuations, and here the black symbols correspond to the AQS stress fluctuation, they are strongly size dependent. And this was the signature of avalanches. Now, when you are at finite strain rate, you lose very rapidly this size dependence. And you might think so. You might think that you lose the AQS in certain way. You lose the AQS character of the dynamics because you strongly reduce. You lose this size dependence of stress fluctuation, which is a signature of avalanches. So, in the next two slides, I'll try to argue about the relevance of AQS. And I will make one misleading statement. You have to concentrate and find what I will say which is misleading. All right? So let's go. So first, we know this from Eshelby. This is the Eshelby field I showed you. So an event, a relaxation event, is a local event. It means you relax a certain strain, finite strain, and take it like that in a certain region. The duration of an event is finite. So you have local rearrangements. We construct a picture where we have the same rearrangement corresponding to a certain strain, a certain size. I'm thinking here in 2D, and a certain time. So the number of rearrangement over a strain interval scales obviously like the strain interval and like the volume of the system, right? If you increase the size of the system, you have, so the number of events, of Eshelby event you see over a strain gamma is proportional to the strain and the volume of the system. And delta gamma is just gamma dot delta t. And now it tells you that the average time between events goes like the inverse of the volume and the inverse of the strain rate. Now, what does it mean to be quasi-static? When I developed the AQS limit, quasi-static means that you see avalanches which are really well separated from each other. You have this elastic loading, and then boom, you have plastic events. So quasi-static means that you have a clear separation of events. So here, this is the rate of energy dissipation. What you see here is an avalanche, and here there is another avalanche, and here you have a time between avalanches. And so when you say you're quasi-static, you want events to be separated in time. So if you think events are just single events, the separation means that the time of a rearrangement is smaller than the time between events, and that tells you that you have a limit strain rate which scales like 1 over L squared. You can do the same thing for avalanches of size n, and then you see that if you consider that to have an avalanche, you need the signal to go through the whole length of your system a number of times. Again, you find a criterion that the strain rate has to be smaller than something like 1 over L cubed. And the problem you have, what you see here, is that these limit strain rate where IQ quasi-static conditions are relevant depend on system size. So that tells you that the AQS conditions are not relevant in the limit of large system for any finite strain rate. So what did I say which is misleading? What I said which is misleading is the last statement. Everything I said before is right. So that's right. This is, you want to separate it, to be quasi-static, you need to have a separation of events. This is how you reproduce quasi-static conditions. You have events which are separated from each other in the finite volume of your system. What I said at the end is that the domain of relevance of AQS dynamics vanishes in the limit of large size. And this is not true for a simple reason. What this is telling you, imagine, for example, you have an avalanche taking place here in a very large system, and the avalanche takes time to develop. And then, when this avalanche is still going on, another avalanche starts here, very far away. This other avalanche is not at all knowing anything about the other avalanche. So the point is that if you take the limit of large system, what happens is that you have avalanches that start to take place concurrently. So you lose the AQS character because you have events that start to occur at the same time. But it doesn't mean that you lose everything about the quasi-static dynamics, because you could have events that occur in you don't need to look only at time in a system of a given size. You need to look at time and space. You need to understand that you're looking at events that you may have events that occur at different places in your system, and that you may have avalanches that are going on concurrently in your system. So, yeah. Yeah.
So is it possible that in the equation in the bottom right, L cube is L?
Oh, it could be, yes, but this is, here I was taking some very conservative estimates. I was trying to do something the worst for me, which is saying that the AQS is really, the range is very small. But it could be something else.
No, I was just dimensionally.
Oh, sorry. Okay. You're right. Dimensionally.
Because this one is.
Sorry. Yes, you're right. The dimension is wrong. Okay, there is a problem. Yeah.
So let's say my question is, if you want the following, is it really normalized over the volume?
Oh, there is an A square which is missing. I'm sorry.
A square. Okay.
There is an A square missing.
A square, and then it's normalized over the volume.
Then it's normalized over the volume. Yeah. Sorry. A square is missing. So you have these. The point is that you have avalanches going concurrently. Let's look at the strain field. If you look at the strain field, and this is for a small strain rate, you see that the events, the strain organizes into patterns. And this does not depend on how large your system is. If you take a very large system, you will continue to see a pattern with a certain correlation. So now, if you change the strain rate, you see a change in this pattern. So what you see is that the length over which, so this is a strain. So this shows you for a strain of 1% where plastic events have been organized. You see at a small strain rate, you see very clear avalanches that almost extend throughout the system. If you go at a larger strain rate, you still see something like a pattern. It's much smaller, but you continue to see something which is strongly organized and strongly correlated. And so you lose the fact that you can separate that you lose the fact that you can completely separate in time the avalanches because they start to occur at the same time. And you can see this because you can see this because if you look at the stress versus strain here, you see you have an event. The black line is the AQS dynamics, and the green line is the same system which is loaded at a finite rate. And what you see here, maybe these avalanches there's something happening. It looks like the stress is ramping up, but in fact, what happens here is that you start to see that you're splitting an avalanche maybe in something here which was just a very flat region of the potential energy landscapes. And so what you see that you have these events start to occur just at the same time, but nevertheless, they do produce spatial correlation. So you have events which are spatially correlated between themselves. So I will, okay, so I will go a bit maybe fast on that. Okay, no, what I want to, okay, the one message. The argument I was trying to formulate before did not work because I was trying to look at a whole system and asking how many events, how I can separate events in a whole system. The way you need to look at the problem is to say, let's look at one region and ask whether it will correlate, whether the question is whether the mechanism of avalanche works. The mechanism of avalanche works when you have a small region which approaches its threshold and can be kicked by the signal coming from another one. And when you do this, and I will pass a bit on the detail, you arrive at the idea that you have, in fact, you can define if you look at the signals coming from a nearby sphere, of course, these signals have a rate which is proportional to the volume of the sphere. And so you can define a length such that the near signal are separated in time. So you have this zone is receiving a short noise from nearby events. And you can essentially show that this corresponds to an avalanche size. So that's where I will pass. You can take diffusion. You can look at transverse diffusion data. And you can get and you can rescale transverse diffusion data. And essentially, the picture we have is that at very low strain rates, we continue to have avalanche behavior. But we have avalanche behavior with an avalanche length which now depends on the strain rate. Okay? So the faster you strain, when you strain fast, because many events happen at the same time, the mechanical noise, the Eshelby signals coming from all these events, they might cancel each other and you lose correlations. When the strain rate is low, if you look at a given region of space, the Eshelby signals coming from nearby region, they are much more infrequent. Because they are much more infrequent, you induce higher correlations. And then what you have is that you have avalanches which are very developed at low strain rate and which are of much shorter size at high strain rate. And so the result of this is that you continue to see something which is akin to the AQS dynamics, but now with avalanches which are rate dependent. Okay? Now, it turns out that I'll pass on that, but we can make a connection between the Herschel-Berkeley law and the fact that you have these avalanches, but I'll pass on that. What I want to really look at is I want to show you what happens when we go towards the liquid. So I want to ask how this whole mechanism is robust now to thermal fluctuation. This is a question somebody asked in my previous talk, but if I add temperature, all these AQAs, these avalanches will be destroyed. So let's look at that. So here I am again in this strain rate and temperature diagram. And so now what we are gonna look at is the first thing we can look at is the transverse diffusion. So I'm shearing a system and I look at the diffusion transverse to the flow. So if you are, the black curve here is the diffusion you get in the unsheared liquid. So here is temperature, here is the diffusion constant, the black line is what you get in the unsheared liquid. Now suppose you take a liquid that you shear at a finite rate. So and let's take here the line with the triangles, for example. So if you shear this liquid at the same rate at high temperature, if you take a given rate at high temperature, you will in fact follow the diffusion of the liquid. And if you cool down, so I imagine I shear liquid and I cool down as I shear the liquid. And what you see is that at some point, the diffusion constant will depart from the diffusion of the liquid. So you shear a liquid at a finite rate. If you shear a liquid at high temperature, slowly, the diffusion you see is a diffusion of the liquid. Okay? Now, if you decrease the temperature, and you know that as you decrease the temperature, the liquid becomes more and more viscous, the dynamics become slower and slower, there is a time when the shear-induced diffusion, so what you see that because of shearing, you induce a diffusion process, and the shear-induced diffusion becomes dominant. So here what you see is the shear-induced diffusion. And here what you see is that the thermal diffusion. So you have a crossover between a regime. So if you look in the temperature and strain rate range, at high strain rate for a given temperature, in the high strain rate, low temperature regime, the diffusion is entirely controlled by shearing. And at high temperature, low strain rate, you recover the diffusion of the liquid, okay? So we are starting to look here at a line which tells us when we are like the solid and when we are in the liquid range, okay? So if we look at the strain accumulation, so here I look again at the strain field, and so delta gamma is the macroscopic strain. So I take a system which has been sheared for 1%, 5%, 10%, and I look at the accumulated strain in a 2D system. Now I'm at finite temperature. I do standard finite temperature simulations. At a very low temperature, you see very clearly and I'm looking at a fixed rate. So here at low temperature, you see very clearly that you have correlations, correlated avalanches. And what is maybe surprising is that here this turns out to be quite a high temperature for this system. It's already close to the TG. You continue to see that the strain map is strongly correlated. Okay? So, if you look at this strain field, so here I'm looking at the strain field, and the way to analyze this strain field, we can look at the fluctuation of the strain field. If you look at those fluctuations of the strain field, you see something that probably some of you have seen in liquids or in diffusion, is that at short time, the fluctuation of the strain grow linearly, and this is just due to the convection by, this is just due to essentially the velocity fluctuation. What you see here is the velocity fluctuation, and it's just the elastic response. What you see is that at intermediate times, the strain fluctuation plateau, and this is a regime where so here what you see that initially you have the fluctuations which are due to the vibration of the system. And then at longer time, you start to see an accumulation of strain, which is a signature of events happening. So here I am looking at a system which is both under shear, it's a liquid under shear at different temperatures. Okay? At short time, you can see, if you look at the autocorrelation of the strain, you can see sound. You will see direct signature that you have here at various temperatures, you see the autocorrelation of strain shows you see here you have what I draw here with the dashed line corresponds to the longitudinal wave sound, and the solid line corresponds to the transverse sound. So if you look at here I'm looking at the very short time fluctuation of strain in the system, and you see sound propagation. Now, if I look at very long time propagation, the strain accumulation at very long time, so here I'm showing you the strain autocorrelation in space at a fixed strain rate, at a large strain of 20%. So I'm looking at a case when I shear enough the system to really produce a lot of plasticity. I'm far from any elastic response. I'm totally dominated by the accumulation of plastic event, by flow event. Here, what I show you is the viscosity of the system. So here is the viscosity. So the viscosity is just, yes?
Those autocorrelation maps, they have like preferential orientation. So
Yeah.
like vertical and horizontal. Is it something obvious?
I'll explain this. I'm just going to explain this. So here what I show you is the viscosity as a function of the strain rate. So this is some standard data. That's just the instantaneous viscosity is just the stress divided by the strain rate. So what you see from the viscosity plot, here you have a very strong shear thinning regime. This very strong shear thinning regime corresponds to simply the fact that you're close to yield stress. And so here you see that you are high, you're at low temperature. So if you look at temperature, these are low temperatures. At low temperatures, you have solid-like behavior with a very strong shear thinning. If you go to higher temperatures, so when you go to higher temperature, the viscosity drops, the system becomes more and more fluid. And at the low temperature, for example, we can take here this 0.4 here, you see very clearly a transition where at low strain rate, you reach a plateau of the viscosity. So this is the Newtonian regime. And here you enter the non-Newtonian regime, right? So this is just to fix ideas. So many different strain rates, many different temperatures, and we can see here completely the crossover between solid flow, very close to threshold, and when you heat up the system, the viscosity drop, and when you are in the right range, you see that you have the Newtonian response at low strain rate and the non-Newtonian response at higher strain rates, okay? So now I will look what happens in the strain field. And so I have here this autocorrelation of the strain field. And so this is the type of autocorrelation we find at very low. Here it's not so low, but that's the kind of autocorrelation we find in the AQS domain. So in the AQS condition, if you remember from last time, we say that when you shear a system in AQS conditions, you have these events, and if you have an event here, that if you have a local shear event, it will produce an Eshelby field, which actually you can see this as the signature of an Eshelby field. I will come back to what it is a bit later. So here you have an increase of the shear stress, and here you have negative lobes with a decrease of the shear stress. So in AQS conditions, these events give rise to avalanches that spread out either horizontally or vertically through your system. That's in AQS conditions. Because I'm using simple shear, there is a technical difficulty, which is that when the system is regularly the system will be, so I use periodic boundary conditions and with a certain strain here. And so what happens is that because of the periodic boundary conditions, these avalanches have difficulty. They cannot just extend by periodicity, and so they have, in fact, to develop some angle depending on the boundary condition over shearing. And because of that, there is a bias between the avalanches that occur along the flow and the avalanches that occur transverse to the flow. Because of this bias, you introduce a screening of the avalanches which are going in the vertical direction. So what you see here is a strain pattern that you would see in AQS conditions. You have the reason why you have very strong positive lobes, again, horizontal and vertical directions. They show you in fact, that you have these, they are the signatures of these patterns where you see you have very long correlations of events here horizontally, but also vertically. So now, here I'm taking a system at a given strain rate and I heat up. So as I heat up, I'm here very close to the threshold. Well, I'm in the solid flow regime, and I'm slowly going here. I'm at the transition between Newtonian and non-Newtonian, and here I'm in the Newtonian regime. What you see is that as you heat up, you lose this very strong correlation horizontally and vertically decays. So you lose, in a certain way, you lose the avalanche character of the dynamics. You lose the fact that events correlate and organize in avalanches. But you continue to see strong correlations of strain. What you see here is a strain produced by a single Eshelby event. So this is what you see here is the signature of independent Eshelby events. And so when you look at the strain as a function of temperature going through in shear liquid, what you see is that up into the liquid, you continue to see again Eshelby events. What is the difference between the solid behavior and the Newtonian behavior is that here, these events correlate strongly along horizontal and vertical directions. The reason they do so is because this is what I was explaining in AQS. When you shear a system, you populate, you bring these regions near instabilities. So you create an excess population of regions which can yield in the direction of the flow field. And this excess population is sensitive to the Eshelby field, can be triggered by the Eshelby field, and will lead to correlation along horizontal and vertical direction. And so the signature of the avalanches here is the fact that if you look, if this is a single event, the signature of avalanches here can be read in the bias between the positive lobes and the negative lobes. When you have single events, the positive lobes and negative lobes have comparable amplitudes. That's the Eshelby signature. Look here. Here it's not as developed as there, but you see that already here you have a bias between positive and negative lobes, which are slightly smaller. And so what this tells you, in fact, and look here, we are just barely in the transition from Newtonian to non-Newtonian. So what this tells you is that as soon as you get non-Newtonian behavior, you start to see correlations between events. So the picture we have, the picture which has been emerging from all of this, is that what we learn from AQS, and again, what we learn from AQS is two things, is you have events which are like solid-solid transformation giving rise to Eshelby fields. That's one thing. And in AQS, these events organize in extended avalanches. these two things continue to exist up into the liquid, up into the non-Newtonian behavior. And so, in fact, what we learn from so with modulo one thing, that the avalanche size might depend on the strain rate, and that as you heat up, you will also start to lose these correlations between events, because in fact, what happens when you heat up is that you may have many thermally activated events which are no longer oriented in this same direction. And so this bias introduced by shear becomes negligible compared to all the other events that happen in many directions. Okay, and so, but so the point is that so what is very surprising is to see a signature of Eshelby in the liquid. Yes. So this has no scale, because I will come to that. This is elasticity.
This is a spatial correlation function, yes, of the strain. So it's defined. So the axis there, for example, vertical.
Yeah.
Then what is that? So what?
So this is the whole system. This is a whole system of 160 particles by size. It's a large system.
So this is the same in all four.
The same in all four temperatures. This is strongly enhanced. The point, I will come back to this, is this decays as 1 over r squared. And so depending on the way you scale the colors, it can look very large, and it has the same pattern at any scale you look at.
If you go to 0.2,
yeah,
and you zoom at the center,
yeah,
you still would see
it's very small. You have a tiny one, exactly. The
difference is that there are two contributions here. One is the self,
exactly,
and one is the
correlation between
the
events.
events.
And here you only have the self. Okay. That's exactly it. That's exactly the point. Yeah. Any other question? Okay, so okay. So there is one thing I would like to draw your attention to. I will also maybe just maybe skip some of the details, but so if you look at the stress, so here I'm looking at the stress versus the strain. So I told you here that the avalanche behavior extends up very high in the liquid, up in the non-Newtonian regime. Now, if you look at the stress, you see something different. The stress tells you another story. The stress tells you that a very small change of temperature causes a very sharp drop in stress, much before you reach the liquid. So here, look, here I'm looking at the temperature 0025, 05, 01, 02. 02 is near the TG. Again, it's 0.25, something like that, TG. So here you have a very rapid drop of stress at low temperature, but the avalanche pattern, which doesn't seem to depend on temperature in the low temperature range. So what happens? And I want to draw your attention to this because I think this is a phenomenon which can be seen in many contexts as soon as you have. So again, it means that if you have small temperatures, and small temperature range is very relevant. If you have a Brownian suspension, very weakly Brownian suspension, you are by nature in a small temperature range. And so you might be dominated by these solid-like features and also with thermal effects that I'm going to discuss. So if you look at stress versus temperature, here you see really stress is very sharply decreasing with temperature. These are for different strain rates as a function of strain rate. So if you look at that, you say, wow, thermal fluctuations are changing everything. But the strain pattern tells you something else. Can somebody guess what happens? So you have the same avalanches at the lower stress. Number is the same. The events are statistically the same at lower stress. So what happens, I told you last time, is that when you approach these instabilities, and each event corresponds to approaching an instability. When you approach this instability, you approach a local yield stress threshold, and when you are near the yield threshold, you have the energy which has a singularity of the energy. Essentially, you reach a saddle node. Now what happens is that if you are at finite t, at t equals 0, this is AQS, you reach instability only, you cause events happen only when you reach the mechanical instability. Now, if you have a small but finite but possibly very small temperature, you may trigger events beforehand. So you may have anticipated events. So you have a barrier, you are driving systems passing through instabilities, and as you drive the system over instabilities, you might trigger, you might have thermal activation kicking in and triggering the system before you actually reach the threshold. So you can model that in a simple way. And again, the idea, and this is a general idea to think about these systems, and this is related to, I told you there are many works by Mathieu Viard in particular and others who are looking at the marginal dynamics. So you are trying to construct mean field models. Here I'm looking at sort of mean field model where I look at one zone which is driven to its threshold. So here is a zone and gamma c is its threshold. And we can look at the probability that it is still in the initial state. So if you are far away from threshold, well, it is here, it's in its initial state. The probability that it is in the initial state is 1. When you are at threshold here, the probability it stays in the initial state is 0. And now you ask, what is the probability? What is the equation governing this probability? And this is just simple rate equation with a rate which is an activation rate. And you work through the technique, and these are technical detail. You can solve and you have nice functions. And essentially you arrive at the fact that basically this activation of a driven barrier causes events to occur, it shifts the threshold. It causes events to occur before the act. So basically, and you can show that this is really stiff. It's a kind of exponential is something really sharply stiff. And it tells you that the activation of a barrier causes a shift of the yield threshold. So it means that all the events that give rise, so you have the same avalanche dynamics, but every event happens before reaching the instability threshold.
Understand. Gamma C is the value that you would have with 0 temperature?
Exactly.
Okay.
That's where this zone would flip at gamma C in 0 temperature condition. But because of finite temperature, it flips earlier, and the thermal effect amounts to a shift of the threshold. And now you can, so if all events occur a bit before, it means you reduce the stress by that much. You basically, you reduce your stress because you're loading elastically up to a threshold, but no, and the threshold goes down. So you're reducing the stress by this factor, and you can then feed your whole stress data. So all the stress, I wanted to insist on this because when you might encounter systems which are, where you think thermal effect don't play a role. Temperature is very small. Even when temperature is very small, at small temperature, you have a singularity of the effect of thermal activation on stress, which is something to know. It's something that actually was shown also in metallic glass by Johnson and Samuel. They took lots of metallic glasses, and they have also, and they saw that empirically, that you have a difference between the yield stress with this T to the 2/3 law, which comes out exactly from this argument up to some factors, but essentially it's a T to the 2/3 law. And so you have, and this is really metallic glass data, and so you see that you have, again, the difference of the, so temperature causes a change of the yield stress, which is down much below the glass transition temperature. So the yield stress is sensitive to temperature, even when you are looking here at the flow of a solid. So we are looking at, yeah, solid flow. All right? So, yeah, so I wanted to arrive here at that. The picture we derive from AQS, that's the message. The message, the take-home message is that this picture persists up into the Newtonian regime. So you have flow resulting from local events, correlate, self-organize. You have spatial correlation up into the Newtonian regime, and you have a stress which is strongly T-dependent at low T due to activation of a driven barrier. And a very important message is the non-Newtonian rheology is the result of correlations between events, right? And this was done in Lennard-Jones models. It's still an active domain of research to understand how these translate, for example, in colloidal suspensions, and where you usually really see these type of systems. And to do this, you need to have better models. And we still don't have the models where we have all the physics, all the right interactions, in order to see whether how all of what I'm telling you extends to, say, a more real-life material. And the problem I think we have is to have to extend that to models which are models of a more realistic colloidal suspension. I wanted just to put this, what I've discussed, all these diagrams in parallel of, I started a talk the other day with this paper by Xu et al., where they show here a map derived from experiments on metallic glasses. And initially, you saw this map. We have the plastic regime with strong and moderate serrations. Here, the non-Newtonian regime, the Newtonian regime. This is exactly what I have described. So we have a very detailed understanding of all this map, of how we have this avalanche size, which is rate dependent in the solid regime. And then we have the non-Newtonian rain transition. And what is really, I repeat myself again, is that in fact, all what we learn from the solid, how solids flow, extends up into the non-Newtonian, and in part in the Newtonian, since we see that events are Eshelby-like events. And the idea of the end of the talk is now to move towards the liquids. So basically, I started from AQS. I've looked at low strain rate. I've introduced temperature. And now I'll remove the strain rate. And because all this, you understand, motivates looking again at liquids. Because we think of liquids, when I started to talk about Eshelby events, and when people talked about Eshelby events in the literature, this was reserved for solids. People, when the idea was introduced of Eshelby transformation, it was about, people were thinking of plasticity in solids. And what you have seen just before is that we have hints that these Eshelby signals exist also in liquids, and the question is why. And it tells us something about liquids, about how liquids, and somehow it's really that we are looking at the liquid from the solid viewpoint.
Before you move to that, I have a question about this framework. And the possibility of transposing this framework into shear amplitude oscillatory test. So, for instance, the experiments that Luca showed in his talk. You start from a solid, and for increasing amplitude, with a fixed frequency, you go progressively into something which has more fluid-like properties.
I don't think so, because when you increase the amplitude, you're really looking at, you can understand this change in amplitude entirely in the AQS context, so in the solid flow. So people speak, I think people misuse a bit the liquid and solid language when you think that you can flow a solid, and that's what I've been showing you. Okay, maybe in simulations, but you have a whole, if you understand that the solid regime is very broad, much broader than one you think, and that you may, if you flow an emulsion, for example, which is non-Brownian, you are really well into this solid regime. And so when you do amplitude tests, you're doing something which is very close to what I was discussing when talking about AQS in the beginning, what people do when they do oscillatory tests in AQS. I would start looking at that. And you can have a solid which is ductile and that you flow and which reaches a steady flow. So I would tend to think of dense colloids emulsions as soft solids that flow by solid mechanisms, which corresponds to what you see here. In order to get there in the actual liquid state, you need to start to have thermal effects which are so strong that basically the system particle atoms are flipping around all the time without any shearing. Maybe the answer is, if your system is, if your particles are not moving in the absence of shear, then it's a solid.
So you said, I don't think so, but probably you want to be the opposite. So it's transposable, what you say, to those experiments.
Oh, it's transposable, yes. Yes, it's okay. Absolutely transposable. It's just that what is transposable is you need to, yes, of course it's transposable, but then you need to know where you are in this diagram. And again, in many soft solids, you are in fact well into the solid state. So you could have thermal effects, as I just discussed, because of activation of the driven barriers. But you could have steady flow and apparent shear thinning behavior. All these are features of the homogeneous flow of a solid.
Just so the glass liquid transition will be when there is no activation barrier in your model, when it goes to zero because of the temperature, or
no? The glass to liquid transition occurs when the rate of spontaneously activated events. When you have say, to simplify, you have an intrinsic barrier height allowing events in the liquid. And when temperature is such that these spontaneous events becomes more numerous, because when you shear, I wrote this kind of technical slide where I counted how many events you need. When you flow, you need a certain rate of events, which is proportional to the strain rate and to the volume. So when this rate is larger than the rate of thermally activated events, then you see that everything is driven by the flow, and conversely. So you are in the liquid where the rate of spontaneous events is larger than the one needed to produce shear. It's not a precise definition. If you look here, when I showed you the, it's sharp and not, well, it's, when you look here at the diffusion, you see you have something curving very strongly on a log scale, so it's not so sharp. At the same time, look that here you have a glass transition in this range, and so, well, you still have no, it's not so sharp, of course. It's the glass transition. You reach the glass transition where everything is time dependent. Okay, so I wanted to get to the liquid. More questions? No? Okay. So I'll move now to talking about the liquid. So it's like a bit another topic, but of course, which is a consequence of that. So I think you all know, you have all seen this kind of diagram, right? Where we see here a glass. So we have here, say, the volume or the energy of a liquid, and as a function of temperature. So here you are in the liquid, and if you cool down, in general, the liquid shrinks. At some temperature, melting temperature reach the crystal, and which also is the volume of which is also temperature dependent. Here you are for just in the supercooled range. So the supercooled liquids, right, are liquids which are below the melting temperature. So they are liquid which are out of equilibrium, which did not crystallize because you brought them at low temperature fast enough. And so once you are in the supercooled liquid range, if you continue to cool down a liquid, the first thing you see that the viscosity of the liquid, here you have inverse temperature, viscosity as the inverse of temperature. You may have a very, first of all, when you cool down, the viscosity increases. It might increase in Arrhenius fashion. It can increase much faster than Arrhenius. This is called fragility. It's an enormous topic in the literature. It's really the objective of many research papers to understand the fragile behavior of supercooled liquids. And then when you continue to cool down, you reach, if you look at the liquid and cool it down, you end up seeing that the volume no longer reduces. And what happens here is the system falls out of equilibrium. So you can no longer equilibrate. If you do a thermal ramp at a certain speed, you will get to, say, you can obtain a curve like that. If you cool down more slowly, you might follow this liquid behavior at a bit lower temperature and then fall out of equilibrium a bit lower. So you have this glass transition where everything is a function of rates, because essentially you have the system is trying to relax, and the relaxation rate of the system are becoming large at the experimental timescales and can be arbitrarily large at experimental timescales. Okay, so I enjoy you to read this once. This is a fantastic paper. This is really, we use all the time, I mean, the fluctuation dissipation theorem. The paper by Kubo is really very helpful, allows you to really understand that. I just wanted to point this out because the way the viscosity is seen in a liquid is so if you shear, of course, you think of viscosity as the relation between stress and strain rate. And the Kubo relation tells you, in fact, that the viscosity is the integral over the autocorrelation of stress. So here you're looking at a sheared liquid. You define viscosity as the ratio between stress and strain rate. You could also consider a liquid at rest. And instead of looking, and you just leave a liquid at rest. And you look at the stress as a function of time, and you look at the autocorrelation of stress. And the integral below the autocorrelation of stress gives you the viscosity. And what you see is that if you take a liquid, so if you take a liquid at high temperature, the autocorrelation of stress drops like that. And if you cool down, you can start to see developing a shoulder, and maybe if you cool down much more, you could see a shoulder extending much farther than that. So here, you see a plateau developing, which corresponds to the elastic behavior of the liquid. And then you have a relaxation. And essentially, so again, the integral below that curve is the viscosity. And so essentially, you can very roughly consider that the viscosity is a product of a plateau value. That's very rough, right? And the time scale. And that gives you an idea of how you get the viscosity of a liquid, right? When you write this, I see people writing Maxwell elements. And okay, we could also discuss what is, but that's the relaxation of a liquid in terms of stress. Okay, so yeah, I wanted to point out you towards this paper. Again, that's a fantastic paper that I really enjoy you to read. This was Luminary. And let's read a bit of what this guy was saying. This was in 1968. A glass at low temperatures, like a crystal, is at or near a potential energy minimum. So Martin Goldstein understood that if you are at low temperature means that this plateau, imagine this plateau extending for a very, very long time. So this fast relaxation is due to vibrations. And the plateau means that at some point the liquid is trapped. And relaxation is extremely slow. It's very viscous because the relaxation is very slow. If relaxation is very slow, it means the number of events per unit time and volume is really very small. And so if the number of events is very small, well, it means the glass is trapped in one of these inherent states we have been talking about from the beginning of this class. It follows that portion, so from other things, he says now, he points out the disorder, and he says that the portion of the potential energy surface that represents the liquid or glassy region has, so unlike the portion associated with crystalline solid, a large number of minima. So because of the disorder, you have these many minima, which we have been talking about, which we see when we do AQS. You jump from a minimum to another one. And he says we will assume a transition over a potential barrier is in some sense local, in that in the rearrangement process leading from one minimum to a nearby one, most atomic coordinates change very little, and only those in a small region of the substance change by appreciable amounts. So he had already this idea that how a liquid relaxes is that the liquid is near inherent states, and relaxation proceeds by local rearrangements. And I did not copy that, but he points to Eshelby. He mentions Eshelby. He says, well, you know Eshelby works, and he says, well, maybe they also interact and talk to each other through this Eshelby field. There is, in the line of this, there is a whole works by Jeppe Dur and his group with basically they coined this word solids which flow. And so they were trying to look for a long time at liquids, saying that in fact a highly viscous liquid is more like a solid which flows. The way they were looking at that is not exactly what I'm talking about. The way they were looking at that is that if you take basically they were thinking of an activated event, and they were imagining in order to have an activated event, maybe you need to expand a bit the volume. But then the solid character is that they say, okay, we need to expand the volume, and then they do an elastic calculation. They say to expand the volume, we need to create a strain, and we calculate the strain field, and then they get the elasticity, and that leads to relating the alpha relaxation time to the shear modulus. It turns out that when you expand, you can see that all the energy is mostly shear energy, and so it leads to a lot of work attempting to relax the alpha relaxation time to the shear modulus. But so again, this is this idea that the relaxation of a liquid, in fact, proceeds by events which are a bit like the Eshelby transformation. So, in fact, you can do this even more than that. What you can do here, when I look at, this is a large system, and here you look at a short time scale, hundreds of the alpha relaxation time. Here that's the displacement field. Here this is the associated stress change field. And in fact, you can see if you look at the shear strain field, so if you look at the change, before I was looking at strain. It turns out that strain is a very complicated observable to define, because what happens when two particles swap their position? I mean, strain is not a very nice observable. For somebody doing numerical simulation, stress is much nicer because it's very well defined. And so what you can do is you can do the stress in one configuration, you look at the stress in the next configuration, you take the difference, and you have stress difference field. And when you look at the autocorrelation here of the shear stress in a liquid, you see a beautiful Eshelby pattern. And so, and you can take a cut through the lobes and you see the 1/r² law. And so you have really, you have elasticity in the liquid. Just look, sorry, I went a bit fast. There's one thing I did not mention. Following Goldstein, if you want to understand the dynamics of the liquid, you only need to look at the series of inherent states. So you have the thermal, you have the liquid which is evolving. You can look at your motion of atoms with all the vibrations, and what you can do, and this was done earlier by De Benedetti and Stirling, you can take your system and quench. So you minimize the energy, and at every time step, you look at the local inherent state. And so you can look at what is the underlying transitions that Goldstein was talking about, these solid to solid transition so this process, hopping process from inherent state to inherent state, you can look at this as transition between inherent states. And so here, this is a change of stress between two inherent states separated by a short time interval. This is the associated elastic strains. And when you look at the correlation of this stress, you see something which is just elasticity. Okay? So I discussed that in the previous talk, that in order, the argument by Eshelby is that you have this inclusion. This inclusion changes shape, and if you remember, the argument was, okay, how do we understand the consequences of this inclusion? And in order to understand what the effect of this spontaneous change of shape, well, you need basically to find the forces that allow you to bring your system back into the initial shape, and then you let go and you have the elastic response. Here, when you have a displacement field like that, you're looking at the inverse problem. You know this simulation tell you that from one inherent state to another, you know what is the displacement field. The question is, can you look at this as a set of Eshelby transformation, as a set of local rearrangements? And so, in fact, the idea is very simple. Well, you can see your displacement field. The idea is you can try to add forces to go back to the initial state. And you're just doing Eshelby in reverse. And so, and these forces, you know, because you know the elastic response of an inherent state. It's governed by a Hessian matrix. And so you can see, for example, here that this whole displacement field corresponds to a series of very local force sets, which really are showing you what Goldstein was thinking, that you have this very local rearrangement and they give rise to large strains. And this is this is in a liquid. And I wanted to touch a bit upon, I'm arriving very close to the end. Oh, I have still a few minutes. So I want to arrive at some more recent things, more recent understanding of how we understand now this elasticity in liquids and this elastic and solid character of liquids. So we start again from this idea that the relaxation of a highly viscous liquid proceeds by local events between inherent states. And so we would like to understand better these inherent states. What is an inherent state? It's again a local minimum. You take a liquid, high temperature liquid, you quench, and you look at this, so you have an inherent state. And here I'm looking at the stress field. And the stress field has it's in 2D. So you have the pressure here, you have the shear stress here, here you have the normal stress, which is the difference between XX and YY. So again, a simple liquid, high temperature, you quench, and this is the stress field. What do you see which disturbs you?
the shear stress is this diagonal.
Exactly. You have very long range patterns. So I'm sure that all the people who have models of, if you look at inherent states, you look at stress fields, maybe it's 3D, it's harder to see. If you have 2D models of whatever, you look at inherent states, and you look at the stress field, and look, what is strange, what should shock you, is that it's a liquid. A liquid is isotropic. And if you look at the stress of a liquid, well, you see that the stress is not isotropic. The shear stress, let's say this is again an inherent state. So this is a disordered solid produced from a liquid. I could produce it by any other means. So I have here a disordered solid. And what I'm showing you is that in a disordered solid, the shear stress is non-isotropic. Does it sound normal? So the reason why this is so, and so you can look at the autocorrelation of these things. And so if you take now, so these are maps. Each of the square is a map, is an autocorrelation. This is the autocorrelation of pressure. You see it has no longer anything. This is pressure and shear stress. This is pressure and, and normal stress, pressure and shear stress. This is the autocorrelation of the normal stress, so which was here. You see this horizontal vertical line. This is the autocorrelation of the shear stress, and here, like that. And all these autocorrelation of stresses present, and if you can take cut, you have 1 over r squared. So you take any solid, and you have this anisotropic autocorrelation of stress. In fact, it turns out that you can prove that this is always true in any disordered solid, in any isotropic solid. And you can show that, I say glasses, but I can say any anisotropic solid, the stress autocorrelation of any anisotropic solid, any isotropic solid is anisotropic. And decays as 1 over RD. So you see, in fact, and this is really a signature of elasticity. This is telling you that the different regions of the system talk to each other and are mechanically balanced. I may not have time to enter into why. Let me just say maybe one thing. The problem is we look at stress in a Cartesian frame. So we are taking stress I just define stress relative to one Cartesian frame. You could also rotate the stress, and when you do that, you have to rotate this tensor. Another point is that if I was looking at stress in 2 frames, which if I have an isotropic system, if I have 2 frames which are aligned, then this is independent of the orientation. So what is really independent of the orientation is the stress in 2 frames which are co-aligned. And now that tells you that when you look at the stress between Cartesian stress between 2 frames, you end up having anisotropies which are really clear. And so now if you, and essentially I will not go into details because I think it's too technical. I just want to draw your attention on that. I will jump to the conclusion. You can show that the stress correlation has a specific form in 2D. It has a similar form. So in 2D, what happened? Maybe I'll go to this. Yeah. Okay. No. Okay. So in 2 dimensions, the autocorrelation stress has that form. So these are 3 stress components. It has this form. Basically the autocorrelation of stress is a transform by some specific matrices of so it only depends on 4 functions. You can show that maybe I'll just go back to that. So so you can show that you have stress anisotropies, you have a large-scale decay, and I'll pass on this because it's the end of the talk, and I'll just conclude. I'll just conclude with this. So why did I want to talk about this stress autocorrelation? Is because this is how now we understand, I think, the why in liquids you have the Eshelby events. Because in fact, in any inherent state, you have long-range stress correlations because of mechanical equilibrium. And so really, when I say solids versus highly viscous liquids, I want to say that we are really looking at liquids from the solid viewpoint. I started from the solid. And initially, what you may have thought at the beginning of this seminar is that, and you asked the questions, is that when what I was looking in the quasi-static limit was really a very strange, bizarre limit, and that all this would be destroyed by thermal fluctuation finite rate. And what we end up at is just the opposite. Is that what we see in the quasi-static limit, which is this solid-like, this flow by solid-solid transformation, is relevant to the highly viscous liquid. So in fact, what happens is that in a highly viscous liquid, the flow proceeds by jumps between these inherent states. These inherent states are mechanically balanced solids. They are solids. And this is the Goldstein view. So a highly viscous liquid flows by transitions, by solid to solid transition, by things which are like the Eshelby transformations. So now what happens is that these inherent states, they display an elastic response, they display long-range stress correlation, they had solids. And then what happens now is that, so now we start from the opposite picture, that in the liquid, you have this relaxation process by Eshelby events. And once you understand this, now it makes sense that when you start to shear, you're just, again, that's what I repeat something I've been saying, but shear starts to force a subset of the events. When you are in the liquid, these Eshelby events can come in all possible orientations. They are shear like that, they are shear like that, you have shear events or changes of local volume, which may happen in all possible tensorial orientations. What happens when you shear is that you start to require the system to undergo, you start to bias the probabilities of events. And as soon as you bias these sufficiently to overcome the spontaneous thermal fluctuations, these events start to talk to each other and start to develop other types of correlations. And the signature of this is non-Newtonian rheology. So in my view, the Newtonian rheology is really the consequence of the emergence of correlations between relaxation events that already exist in the liquid. Okay? And I think I'll finish with this.